Let us begin. So, when you are introduced to set theory, naive set theory in high school, then usually we study sets with relations and functions. So, today's topic is binary relations. So, you have already seen this. We have borrowed the term relation from real life. We have relatives. X is the mother of Y. Is that a relation? Yes. It is a relation between what? Can you tell me? The set of people on the planet and the set of people on the planet. Correct? Okay. Now all of you are carrying backpacks. Maybe some of you are not, but like X is the backpack of Y. That's a relation between set of backpacks and set of people. So similarly, binary relations, they need not be defined on the same set. They need not be homogeneous. So R subset of A cross B is a relation from A to B. If A is equal to B, then we say R is homogeneous. Otherwise, heterogeneous. Okay, so very simple. I'm just going to throw lots of words today. I'll give you some examples, but today is a lecture on glossary of order theory. Glossary as in lots of terms. Okay. So, whenever we are given this, especially if A is not equal to B, then we are interested in the converse of the relation sometimes. So, converse of R is defined to be, I'm just going to say R op. It is defined as those pairs B comma A in B cross A such that A comma B belongs to R. So if A comma B, if A is related to B using R, then B is related to A using R op. Very simple. So this is a subset of what? This is a subset of R? No. The subset of B cross A. Very good. Okay, so R op is defined here, and we have already seen one example of a converse or a dual. Yes, when we are talking about linear orders, then we said star, omega comma belongs to star. That is the inverse. The invert all the order relation. Okay, good. Then if R1, if R is a subset of A cross B, then the complement of R is what? What should be the complement? Tell me.
A cross B minus R.
Very good. And we denote it by R bar. A cross B minus R. Well, okay, do you want me to do any examples of these things? These are very simple things. We are not in high school anymore. That's why I will do more examples when we will talk about some special relations which are partial orders. Right now let's just do this. So if R1 and R2 are relations from A to B, then so are, yeah, pun, so are R1 union R2 and R1 intersection R2. No confusion over here, simple, okay. Now the next thing, if R is a subset of A cross B and S is a subset of B cross C, then define the composition S composed with R as the set of, please tell me, set of all A comma C in A cross C such that there exists a B, some B in B, such that A comma B is in R and B comma C is in S. So basically they are connected by through some element of B. That's the simple composition. Okay, then if A prime is a subset of A and R is a subset of A cross B, then the restriction of R to A prime is, I mean we'll denote it by this, R restricted to A prime. What should I write? A comma B such that A belongs to A prime, B belongs to B, okay, and A comma B belongs to R, which is also, I mean we can simply define it as A prime cross B intersection R. That is the restriction. Now I am just going to say if B prime is a subset of B, then the co-restriction is, yeah, I mean R restricted to B prime, you simply make it A, this is B prime, and this will be A cross B prime intersection R. At the same time you can do restriction and co-restriction both. Okay, in this part no examples, but because these are all simple things. Any questions about this? So mostly we will only deal with homogeneous relations, and we already know several examples of homogeneous relations. Yes, the first one, it was linear orders. Linear orders are homogeneous, they are binary relations, and we have also seen partial orders. So just to recap it quickly, a partial order, partially ordered set, a poset, yeah, is a reflexive, transitive and antisymmetric binary relation. Then we have also seen that from a weak partial order we can get a strict partial order, and from a strict partial order we can get a weak partial order just by removing or adding the diagonal. So we are going to not make any distinction, but we will use this notation, yeah, A less than B. Whenever we say, then that means A is less equal B and A is not equal to B. Okay, so give me some examples. Examples of partially ordered sets. Any ordinal, okay, very good. So alpha comma belongs to in On. Okay, very good. These are partial orders. Are they weak partial orders or strict partial orders? Yeah, these are strict partial orders, but you can define the corresponding weak version. Yeah, beta belongs to gamma or beta equal to gamma, that is beta less equal gamma. Okay. Then any other examples? Order relations are present everywhere. Yeah. Subset? Okay, so consider power set of X with respect to subset relation. A is a subset of B. Yeah, that is a partial order because A is a subset of A. It is reflexive. If A is a subset of B, B is a subset of C, then A is a subset of C. And if A and B are both subsets of each other, then by which axiom of set theory? Extensionality. Very good. So therefore this is also a partial order. Any other examples? All real like all real examples, Q less than, R less than or less equal, correct? Then one more interesting thing is natural numbers with divisibility. So what is the relation? So let me write that down. So A meet B, A divides B is read as A divides B. Okay, if I define this, then let us verify. Does A divide A? Okay, if A divides B and B divides C, then does A divide C? Yes. Okay, what is the meaning of divides?
There exists C that such a is equal to,
i.e. there exists a C in N such that B is equal to AC or CA, doesn't matter, the multiplication is commutative. Okay, and please observe that I am taking all natural numbers, and in this course natural numbers include 0. Okay, good. Then is it antisymmetric? If A divides B and B divides A, then A is equal to B? Okay, good. Now what about Z divides? Is this a partial order?
no, you can have associated.
Why no?
Like minus 2 and 2.
Minus 2 divides 2, 2 divides minus 2, but minus 2 and 2 are not right. So this is not antisymmetric. Such a thing is actually called a pre-order. Yeah, pre-order is reflexive plus transitive relation, but that is not necessarily antisymmetric. Pre-order, or in some literature you can also find the name quasi-order for this. Okay, then you are studying vector spaces. So from vector spaces I have one more example. Yeah, so that is all subspaces of a given vector space with respect to containment or subspace relation, maybe let me call it subspace relation. Yeah, subspaces with respect to subspace relation. So by this subspace relation is nothing but just subset. Yeah, the only condition is that our domain is restricted. We are not talking about all subsets of a given vector space. We are only talking about subspaces of the given vector space. Okay, very good. So this is interesting. Then if I draw something like this, these 4 elements, and they are related like this: A, B, C, D. Is this a partial order? Okay, whenever I draw this, then you should first ask me the question, what does this mean? What does this mean? Yeah, I mean, it is simple. Whenever an element is connected by a vertical line or a slant line, then that is strictly less than relationship. So that means A is less than C, A is less than D, B is less than C, B is less than D. Strictly less than, yeah. The equality relations you can already understand. So now tell me, is this reflexive? Is this reflexive?
Yeah.
Yes, yes, okay. Then is this transitive?
Yeah.
Yes. Is this antisymmetric? Yes, it is antisymmetric. Yeah, there is nothing to check there. No line is going like, it's not confused line. It's always going from a lower element to a higher element. Yeah, I am not drawing a circle anywhere. Yeah, so as long as I am not drawing a circle, this is okay. Then this particular poset will also be of our interest. I am going to name it as per my wish, and these names will be clear later on. I prefer to call this the two crown, and the standard name for this is M3. Okay, so M3 has three elements which are pairwise incomparable, A, B, C, and then one least element, one largest element. Okay, this is also a poset. Yeah, it should be easy to verify. M3 is also a poset. Then one more thing which I will need at a later point is this pentagon picture. This is 0, A, B, C, 1, and this is called N5. This is also a partial order. Yeah, what is the condition here? See, A and B are not related. So A comma B and B comma A, neither of those two elements are in the relation. Yeah. Similarly, A and C, they are not related. Okay. Then this one is also interesting. Let us draw the simple one. This is either M2 or it's also power set of two elements. Yeah, power set of two elements. Can I write that? So the empty set here, then singleton 0 over here, singleton 1 over here, and 0, 1 over here. So what is the line? The line represents strict inclusion, strict subset relation. Now we have been drawing these diagrams. These diagrams have a name. They are called Hasse diagrams. Okay, after a German name, Helmut Hasse. So, if you are done with this page, I am going to.
Sir,
Yes.
like they should be the directed.
The direction is from a lower level to upper level, always. Yeah, so that's why direction is not being written. Okay. So let us study Hasse diagrams named after Helmut Hasse. Okay, so for that we will need the concept of an interval. So given a partial order poset T less equal, and A comma B in P define the interval, the closed interval AB. What should it be? Closed interval AB. All those elements in C in P such that A is less equal C and C is less equal B. This is our usual interval, but whenever we think about intervals, especially in real numbers, then they are linearly ordered. Whereas the intervals here, they need not be linearly ordered. So for example, let me go back to the previous thing. So what is the interval from 0 to 1 in M3? The interval consists of everything. Because 0 is less than all of these elements and these elements are less than 1, so therefore, and 0 is less equal 0 and 0 is less than 1. What if I consider the interval bit from A to 1? Only A and 1 will appear there. Okay, so therefore now you know what the intervals are. So intervals are not necessarily linearly ordered. Okay, so similarly define open interval. What will be the open interval? All those C's in P such that A less than C and C less than B. So no equality allowed at the boundaries. That is our open interval. And well, semi-open, semi-closed also you can do. On one side it is closed, on another side it is open, so that's easy. So now say that B is a cover of A if the interval AB is only consisting of two elements and A is not equal to B. Okay, so cover means that it is immediately above it. There is nothing in between. In other words, there is no C in P such that A less than C and C less than B. Okay, so if you understand this, then please tell me what are the covers in here. In this 2 crown example, C is a cover. C is a cover of A, C is a cover of B, D is a cover of A, D is a cover of B. So there could be multiple covers and one element can cover multiple elements, right? So this is a many relation, not necessarily unique. So actually, I mean again look here, is 0, 1 a cover of empty set? No, because there is something in between. So basically whenever I draw this line, then that means there is a cover. So basically what is Hasse diagram? So Hasse diagram is shows covers. That's all. So for example, I can write down omega less equal, I am using this notation, then I can write it down. How? I will write 0, then I will write 1, then I will write 2, then 3 and so on. This is a Hasse diagram for omega. Can you draw Hasse diagram for rational numbers? Because they are dense. Okay, so we cannot draw them for rationals. For reals we cannot draw them. Usually Hasse diagrams are reserved for finite posets, or they have some nice properties. Yeah, there should be no density. That's the most important thing for drawing them. Okay, then whatever we had on the previous page, that was also Hasse diagram. Then what about n divides? Can we draw the Hasse diagram for n divides? Yes. Please tell me how. Does there exist a least element? 1. 1 divides everything. Very good. Then what about 2? 1 divides 2? Okay, good. So I am writing 2 and there should be an arrow. What about 3? All the primes. Very good. 3, 5, 7 and dot dot dot. Then what will be the next level? All composites. All composites on the same level?
All evens.
All evens.
Single prime powers, like.
Yes.
Single prime powers.
Yeah, like where the degree of the prime is 1.
Okay, I'm still not getting the right answer. It is products of 2 primes. So it could be 4, it could be 6, it could be 10, it could be, it cannot be 8 yet. Okay, so 2, 4, yes. Then this one, sorry, not this, 6, 3, 2, 6, this, then 15 and so on. And does there exist a maximum element? Yes, there does.
0.
Yes. 0 lives at the top. Okay, so this is our Hasse diagram for the divisibility lattice. You can draw divisibility lattices for divisors of a given number. Yeah, they will have beautiful pictures. Right. So this is our Hasse diagram and you can only do it in a certain case. Okay, I have been asking you some questions. Yeah, does there exist a maximum element? Does there exist a minimum element? Let us define them. So, say that M in P is the minimum element if for all A in P, M is less equal A. So it should be comparable with every single element and it should be lower. Okay, what will be the maximum if for all A and P everything else is same? M bigger equal A. Okay, so the definition is easy. I am switching my slide. Okay, tell me, alpha belongs to, does this have a minimum element? Yes or no? Yes. No, that is a wrong answer. See, what if it is 0? If alpha is 0 itself, then it doesn't have a minimum element. If alpha is non-zero, then it has a minimum element. Please be aware. Okay, if alpha is non-zero, then this has a minimum element. And does this have a maximum element? Not always, but when? If it is a successor ordinal, then it must contain a maximum element. Okay. Then what about the power set? Does it have a minimum element? Yes. What is the minimum? Empty set, no phi. Empty set. And what about the maximum element? X. Rational numbers, minimum doesn't exist. Maximum? Real numbers, minimum No minimum, no maximum. Natural numbers with divisibility. 1 and 0. Okay. Then subspaces of a vector space. Maximum, the whole vector space V itself, and minimum 0. Yeah, not empty. The 0 subspace. Okay. What about this thing? Minimum empty set, maximum 0 1. Crown. Minimum, no minimum, no maximum either. Okay. M3 and N5 both have minimum and maximum. Yeah, the minimum, if it exists, then it is traditional to write it using 0. And the maximum, if it exists, then it is traditional to write it 1. But, yeah, I mean, be aware, in divisibility lattice, 0 is 1 and 1 is 0. Okay, so, but I mean, when we will study lattices, then 0 and 1 are standard notations, not for partially ordered sets. However, this 2 crown is an interesting example. It doesn't have a minimum element, rather it has minimal elements. So say that M in P is a minimal element if for all A in P, A less equal M implies A equal to M. If there is a lower bound of M, well, then it is M itself. There is no strict lower bound of M. And what will be a maximal element? If for all A in P, A bigger equal M implies A equal M. Okay, so if M is the minimum, then it is the unique minimal element. Right? It is the unique minimal element. There may or may not exist any minimum or minimal elements. Okay, and if M is the maximum, then it is unique maximal element. Yeah, please do not get confused. Minimum, if it exists, then it is unique, and minimal, even if they exist, there could be multiple of them. So for example, now consider n plus, which means positive natural numbers with divisibility. What are the maximal elements in this? Yeah, this has no. Yeah, this has no maximal elements. But does it have a minimal element? Minimal is 1. Okay, then what about I remove 1? I remove 0 and 1 and I just consider this. Then what are the minimal elements? Yes. Has primes as minimal. But no maximal elements. Okay, very good. So these definitions are sorted. Yeah, if A is less equal B, then we say that A is a lower bound of B and B is an upper bound of A. Lower bound, upper bound. Yeah, simple. Okay, then define the downset of A to be all those B's in P such that B is less equal A. Anything hard about this? Downset of A. And what will be the upset of A? The collection of all upper bounds, which means all those B's in P such that A is less equal B. Okay, let me go here. What is, so if I give you this particular point A in the 2 crown, what is its upset? I hope you are not upset with the word upset. Huh? I always make this joke in every class. Okay. A, C and D. Yeah, these are the upper bounds like this. Okay. Then what about B? Okay. The least upper bound of 2 elements is the least upper bound, which is common to both of them, right? It is a common upper bound of both of them, and it should be the minimum such. Now, what about A and B over here? Do they have a least upper bound? What are their common upper bounds? C and D. And is there a least one among C and D? So therefore they do not have a least upper bound. Okay, so let me continue with the definitions. Given S subset of P, say that A is an upper bound of S if A is if for all S, little s in S, we have S less equal A. So we are not talking about just an upper bound of an element. We are talking about an upper bound of a subset. Okay. So similarly, I can define a lower bound of a subset. Then I can define the collection of all upper bounds of S, all those A's in P such that for all S in S, S is less equal A. And I can define downset of S, all those A's in P such that for all S in S, S is bigger equal A, or A is less equal S. Now given, let's see if you can figure this out. Given S subset of power set of X, describe downset of S. So S is a collection of subsets of X. Okay, so what should be the downset? Downset of S. Does there exist a single element in the power set whose downset is equal to this? Now if I write it, you will
Union.
D of
Union.
not union, it's a downset.
Oh, intersection.
It is intersection of S. Okay, let us do this exercise. So let x be 0, 1, 2 and S be, I will take 0, I will take 0, 1 and I will take nothing else. Okay, just these two elements, 0 and 0, 1. Then what is downset of S? What is downset of S? What are common lower bounds of elements of S? Singleton 0 and
0.
empty set. And is there anything else? Is singleton 1 here? Singleton 2? No. Yeah, nothing else is there. Okay. But this is also the downset of singleton 0. Okay, let me quickly shift to the previous slide. Observe what is the downset of a of an element. It is all those b's which are less equal a. Okay, so come here, right? So actually this is known as a principal downset. A subset D of P is called a downset if for all B in D and for all A less equal B, A belongs to D. So what is a downset? I mean, the proper name is actually downwards closed subset. Whenever it contains an element, then it must contain all its lower bounds. Understood? Whenever it contains an element, it must contain all its lower bounds. Let me go to an example. So for example, the set of divisors of 25 is a downset in n divides. Observe why. Suppose n is a divisor of 25 and m divides n, then m also divides 25. Yeah, simple thing. So it's a downset. So what are standard examples? Well, downsets, these ones. Yeah, these downsets are always downsets. Like the downset of S is a downset. For any S subset of P. Okay, maybe you are confused. Let me remind you what I am saying. S was a subset and then I defined the downset of S. Now what I am saying, that the downset of S is also a subset of P. and that is a downset on its own. This is the downset of S is a downset. The upset of S is an upset. But in English, down also means, if somebody is down, then that means they are upset. So downset and upset don't really mean anything different in English. But in maths they mean something different. Okay. Any doubts about this? You are getting what is a downset? Okay. Then a downset is a principal downset. Downset D is a principal downset. Sorry, I'm making a mistake here. Principal downset. The other principal stands for a rule, This is a principal downset if there exists an A in P such that D is equal to D of A. It is precisely the collection of all the elements less equal a fixed element. Then it is called a principal downset. So for example, let me go back to this example. So if I take, maybe I will use red color. So upset, upset of A intersection upset of B in this crown example, is this a principal upset is equal to C comma D and is not principal, is not a principal upset. Okay, I will ask you some examples over here. If I give you this, is this a principal downset? Everything below this red line over here. Is this a principal downset? No. Why?
It's not generated by anything.
It's not generated by a single element, right? There are, so A and B, they are incomparable and they are maximal elements in this subset. If it is a principal downset, then it must contain a maximum element. Okay. What about this? This is a principal downset. What about this? This is a principal upset. Okay, so you are getting the hang of all these concepts. Okay, one last definition perhaps for today. Given a poset P less equal and say that S subset of P is a chain if, now see, S subset is a chain if it is linearly ordered with respect to, if any two elements, if any two elements of S are related by less equal. In other words, S comma less equal intersection S cross S is a linear order. So I restrict my order relation only to S. Then it is a linear order. So for example, the set p to the power n, where n is in n plus, is a chain in n divides for any p. For any p, all the powers of a fixed number, that is a chain, because given two different powers of p, either this divides this or this divides this. So therefore they are totally ordered, or they are linearly ordered with respect to the order relation. Let's stop here.